Okay, let me give you guys another example. So suppose you're asked to find an equation for any line such that the gradient at any particular point on that line is twice the gradient of a line that joins the origin to that particular point. Okay, so your job here is to come up with an equation for this line such that any point on that line, let's say here, then the gradient at this particular point is twice the gradient of the line that joins the origin to this particular point. So for example, at this particular point, x, comma, y, the gradient of, you want to come up with an equation for this line such that the gradient at this particular point, such that the gradient of this line here is twice the gradient of the line that joins the origin to this particular point. Okay? So to do this here, your job here is to come up with an equation of y equals some blah 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 for this line here, such that the gradient at this particular point, well, the gradient at this particular point is dy by dx, such that it is twice the gradient of this line here. So what is the gradient of this line? Well, the gradient of this line will be the up and down here divided by the across here. Well, the up and down here is y, and the across here is x. So you want to come up with an equation for this line here. So you want to come up with an equation for this line here, such that dy by dx at any particular point on that line will be twice the gradient of this line here. Well, the gradient of this line will be y over x. Okay. To solve this problem here, set up your differential equation. Well, this here is your differential equation. You want the gradient at any particular point on that line, such that it equals twice the gradient of the line that joins the origin to that point. Well, your differential. So given this situation here, your differential equation should be this. So set up your differential equation, which will look like this, and then separate all the variables. So all the y's goes on this side, all the x's goes on this side here. So separate all the variables. That will then take you to here, and then now integrate equally to both sides. So from here, integrate this side, and then integrate this side here. So when you integrate, you're actually looking for something such that you're looking for this thing here, such that when you differentiate it, it will give you this thing here. And then on a separate occasion, for this side here, when you integrate this here, you're really looking for something. You're looking for this something here, such that when you differentiate it, it will give you this thing here. So when you integrate this here, you're actually looking for something. When you differentiate it, it will give you this thing here. Well, from the uniqueness theorem, if you have something that differentiates, so from the uniqueness theorem, if you have two things that differentiates to the same thing, because of this from the uniqueness theorem, if you have two things that differentiates to the same thing, then these two things must be exactly the same but only differ by a constant. So what we're saying is that this must be exactly the same as this but only differ by a constant from the uniqueness theorem. Okay, so when you get to this stage here, integrate equally. So when you get to this stage here, on one occasion, you're trying to search for something that when you differentiate it, it will give you this thing here. And then on a different occasion, you're trying to differentiate. You're trying to search for something that when you differentiate it, it will give you this thing here. Now, from the uniqueness theorem, this must be equal to this. Well, if you find the antiderivative of this, it will be natural log of y here, and then over here it will be 2 natural log of x. So this must, well, plus c here, and then plus c here. So from the uniqueness theorem, hang on, let me just do this step once more. So when you're here, you're trying to find out the antiderivative of this. So you are looking for something that when you differentiate it, it will give you this. As it turns out, it will be natural log blah 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 plus c. And then antiderivative of this is you trying to find something that when you differentiate it, it will give you this. And it turns out to be 2 natural log of x plus c. Now you've got so when two things differentiates to the same thing because of this equal sign here, then this must be the same as this, but only differ by a constant. So that will then allow you to get to here. You've got a C here and C1 here and C2 here. You can combine the two together and just call it a new C. So from here you can get to here. Okay, and then exponentiate both sides. So e equally to both sides. So that will then take you to here. Okay, and then looking at this part here, looking at this part here, if you have x squared, okay, so suppose you've got x squared. If you natural log x squared, then this 2 here will come down here. So hang on. So suppose you have x squared here. Natural log this, that will become that will then become this. Okay. So when you have this here, you can rewrite it as this. Okay. So because this is exactly the same as this. So the point is, at the moment it's like this, but rewrite it as this. So now now these two are inverses of each other. You've got an e here, you've got the natural log here. They're inverses of each other. Bear that in mind. Okay. So hang on. So from here, rewrite this as natural log of x squared. Okay, and then you've got this thing here. So using this here, that will then take you to this. But this here is just a constant that you don't care about. So let's call it capital A. So here you've got times capital A here. And then we'll tidy it up, move this capital A over here. That will then take you to here. Okay. Now looking at this here, you've got E and then you've got the natural log here. They cancel each other out, giving you y equals a x squared here. I will continue in the next video. So anything in, well, actually I'm going to finish it now actually. Y equals anything of this form here will give you well, if you select any point, let's look at y equals x squared here. So the point here is that anything of this form here will satisfy our problem. Okay, looking at this here, if you select this point here, the gradient of this point here will be twice the gradient of this point here. Okay, looking at y equals 3x squared, let's say this point here, the dy by dx of this thing here will be twice the gradient of the origin to that point there. Even when a is -2, at this point here, if you look at the gradient here, that will be twice the gradient of this. So this here is your answer here. Okay.